Alright, so where we left off last time, we were looking at making these ice channels. So here we have another reaction. We have COBr2 in equilibrium with carbon monoxide and bromine gas. If I know that the equilibrium constant is 0.190, the question is, what are going to be the equilibrium concentrations given the equilibrium constant, and that I know that there's initial concentration of COBr2, which is 0.250 molar. So what we're going to do is we're going to fill in our ice chart. So we put 2.50. That's the only initial concentration we have, so we put zeros in for that. So as we see the change, we are going to lose some amount x, and whatever amount we lose over here, we gain over here. So the equilibrium is just the 2.50 minus x, and x. So now we're ready to solve for our equilibrium constant. So we know it's true that K for this equation is 0.190. So then we have the concentration of products over the concentration of reactants. Then we fill in what we have from this table up here. So from our table, we know that we have x over 0.250 minus x. So if we simplify that, we now have x squared over 0.250 minus x. So let's start to simplify that. We have 0.190 x squared 0.25 minus x. So first step is to get this out of the denominator. Then we multiply that through. And we get all the like terms on one side. And at this point, you should recognize that I just wrote out a quadratic equation, which means we now need to use the quadratic equation to solve for the answer. So, just as a reminder, right, the quadratic is ax squared plus bx plus c equals 0, which we usually rewrite in order to solve for x, minus b plus or minus the square root b squared minus 4ac over 2a. And now we just plug in from our quadratic equation these values. So in this case, a is 1, right, the implicit 1. B is 0.190, and C is negative 0.0475. So we can go ahead and plug that in. I'll scoop this up so we can all see. So I now have x equals negative 0.190 plus or minus square root 0.190 squared minus 4 times 1 times negative 0.0475, all divided by 2 times 1. So, simplifying this, multiplying it all out, do subtraction, we'll get to this point. Right, and because we have this plus or minus, we'll get two different options of what x could be. 0.190 plus the square root, or 0.190 minus the square root. So our x options are negative 0.332, or x equals 0.143. Now, let's think about what x was supposed to be. X is a concentration, which means it's a molarity, which means the only reasonable answer is this one. Because we can't have a negative molarity. So we're not done. we need to figure out what the equilibrium concentrations were. So going back to our ice chart, we can see that for both carbon monoxide and the bromine gas, we're done. That is X. But for the COBr2, it was 0.250 minus 0.143, which means its equilibrium concentration is 0.107, which would make sense because it was a reactant and it's going to lose this amount to make this new value. All right, so let's do another one. Let's say I have PCl5 in equilibrium with PCl2 or PCl3 and chlorine gas. Again, we're going to make an ice chart using this information given and find these new equilibrium concentrations. All right, so first thing we need to do is set up our ice chart. So we get a piece of paper to set that up. I haven't already written on. Here we go. Okay, so here we have our ice chart. Alright, so we are again going to start off with that and none of products. Lose this much, gain. Oop. So just like the ice chart we had before. So now we're going to set up equal decay. 1.2 equals x squared over 0.300 minus x. So rearrange it so we're in terms of x squared multiply that through. So then we get into our form of the quadratic equation that we can then use to solve in our quadratic equation formula. So b is that, so minus 1.2 plus or minus the square root of 1.2 squared minus 4 times 1 times negative 0.36, all divided by 2 times 1, but that just is 2 again. All right, so then doing some simplification. We get to the point we have our two options of x. X could either be negative 1.44 or x could be 0.248. And again, it has to be a positive number because it's a molarity, which means we have this as our value of x, which means our equilibrium concentrations of PCl3 are equal to each other and equal to 0.248. And then PCl5 is 0.300 minus 0.248, which gives us a final value of 0.082 molar. All right. So that's how I set up those problems to figure out the final equilibrium concentrations. So looking ahead to the next section, there's a good practice problem you can do on your own, setting it up and solving it. Slightly different in that I have two reactants. and one product, but I give you the final molar of this, and we figure out what it is back that way. So how do we then use the equilibrium constants when we have different concentrations? And how does that affect K? So here I have, right, we'll look at one part at a time. So I have nitrogen reacting with 3 hydrogens to make 2 ammonias. So if I wrote the equilibrium constant for that, I would write K is NH3 squared on top, then my products, which is my products, then my reactants are on the bottom, 1 nitrogen and hydrogen cubed. And that is my equilibrium constant. But what if I use different stoichiometric coefficients, right? What if I doubled it? Now I have 2 nitrogens and 6 hydrogens make 4 NH3s. Well, if I rewrote my equilibrium constants, right, we would have NH still on top, NH3 still on top, now to the 4th power, over N2 squared and H2 to the 6th. Well, I can simplify that, and really I have my original equation squared, which means I simplified all of these by 2. Right, and so then 2 squared is 4, right, and then 6. Which means I've taken this equilibrium constant and squared it, which means when I double the stoichiometric coefficients, I square the equilibrium constant. So how does that come out to some rules about how we can make predictions using our equilibrium expressions? So when we have stoichiometric coefficients in a balanced reaction, are changed by factor n, just like we did. We had one reaction and then we doubled it. This doubling is going to be a factor. So we went from this amount and we squared it, or we doubled it, so then we square it. If we tripled, we would then cube it. If we write the chemical reaction in reverse, it's going to be 1 over, and if we combine several balanced equations to make a new net balanced equation, the equilibrium constants are multiplied by each other. So let's take a look at how that plays out. All right, so calculate the net equilibrium constant for this reaction, iron and water making ferric oxide and hydrogen gas, given 2 equations. That's very similar to what we did when we did enthalpy. We have delta H, and depending on how we need to use the equations, we're either going to flip them, reverse them, and then that affects how we use this K value. So I know I would need iron as one of my starting materials, so I'm going to use this equation, but I'm going to rewrite it so that iron is the starting material. All right, so now that I have reversed the direction of the equation, I now have to go 1 over 0.67, which is equal to 1.49. And then this other equation I can use as is. And since I use the as is, I'll just leave the equilibrium constant as given. So now I can write out my new net equation, canceling out anything that shows up on reactants and the product side. So carbon dioxide and carbon monoxide, which gives me my final net reaction, which is what I wanted. And then these 2 K's, using our rule, in order to get the K net, we multiply them by each other. So the net is is equal to 1.49 times 1.6, which is equal to 2.4. So let's do one more. Let's say I have this information. The net I'm aiming for is this. So I'm looking for the net equilibrium constant for this reaction. So what I'm going to do is I know I have these two possible reactions to combine together. I'm going to this K is much greater than 1, so just side note, this would go towards reactants. Then I have this other reaction. Let's see, how do I have it written out? I'll do this. Okay, so those are my two possible reactions to use. So looking at how I want to use it, I can see that definitely I want to use this first one, but in reverse. I want to use it like this. So the K for that is now going to be 1 over times 10 to the 5th. Then I can use this other one as is. So starting with that, I can see that my new net equation would be CO2 let me think here. Something is not right. Oh, I know what it is. Right, this is too many. I don't want 2 COs because that would leave me with an odd number of carbon monoxides on that, on which there shouldn't be any carbon monoxides in my final equation. So I need to figure out how to get rid of all of these. I need to take them all down by half. So I take them all down by half. I raise that to the power of 1/2. So now I have my new equation for that is now CO and 2 hydrogens makes 1 methanol. So my new net equation using this equation and that equation works out much better. Now I have carbon dioxide and 3 hydrogen gases make 1 methanol and 1 water. So my K net is equal to 1 over 1 times 10 to the negative 5th, or positive 5th, times 2.8 times 10 to the 7th, to 1/2 power, which would be the same as square rooting. So that is really 1 times 10 to the negative 5th times 5,291. So that would be our final K net. So it's very similar to stuff we've done before, just using slightly different rules than we used with enthalpy and a few other similar types of problems, where depending on if you flip it over, you do 1 over. If you have to divide it through, you take it to that power. Overall is multiplied together. So let's talk about how changes to the system affect our equilibrium constant, which you're probably familiar with Le principle. But you may not have used it in context of equilibrium constants. So, any change in any of the factors that determine the equilibrium conditions will cause the system to change in such a manner to counteract that change. So systems always want to be at equilibrium and will do what it takes to get back to a position of equilibrium. So let's see what I have. All right, so let's look at an example and we'll see how that works out for us. So here's my example. I have 2 sulfur dioxides and an oxygen in equilibrium to make 2 sulfur trioxides. Now, a piece of information they give us is that the delta H for reaction is negative 197 kilojoules for this reaction. So if it's a negative delta H, that tells us it's exothermic, which means it releases heat. So let's look at the different ways we could determine things about this system. So I don't know if I'm at equilibrium, right? I want to know how equilibrium and equilibrium constant are related. So I can write out the reaction quotient for this. Which it's more appropriate to write gases as pressures. So you'll often see in your textbook, or I'm mastering, something more like this, where it's saying, really, we don't measure gases in molarity. Brackets really mean molarity. It's more appropriate to measure them as pressures. So, at equilibrium, Q equals K. As a reminder, right, if Q is less than K, it'll proceed to products, or it'll shift right. If Q is greater than K, it'll go in reverse. It'll proceed towards reactants, which is what we had, how many slides ago? There we go. Make more reactants, make more products. All right, so let's look at some things that could happen to our system and what will happen to the reaction. So let's say I add more sulfur dioxide. I now add more of the denominator. So the denominator is going to get larger in Q versus what it should be in K. And so if the denominator gets larger, this whole numerical value gets smaller, which means Q is getting farther away from K. So if I add more SO2, Q is less than K, which precedes the products. Which you could have guessed, right? I'm going to add more reactants. It should shift it to more products. But now let's take a look at if I removed oxygen from the system. So now I'm going to make this value smaller. If I make that smaller, it makes the denominator smaller, which makes the fraction larger. So now Q is going to be greater than K, which means it's going to proceed towards reactants, which again, you could see if we remove oxygen, it's going to push this reaction back this way to go back to a state of equilibrium. Well, what if we decrease the volume of our container by half? That's going to be harder to look at. So let's look at our Q equation. So if I decrease the volume by 2, I'm saying I've increased pressure. right? Using our ideal gas law, PV equals nRT. So if volume goes down, pressure has to go up. If we increase the pressure, we have provided increased pressure, less space for the same reaction. And we're going to go towards the side of the reaction that has the least moles of gas, because we have less space or increased pressure, so we want to have the smallest number of moles in our reaction flask. So the reaction will move towards the side of least moles or least molecules. So if we look at our original reaction, I have three total moles over here. And on this side, I only have 2 moles. So 2 is less than 3, so the reaction is going to shift to the right. Or we'll shift towards products. Okay, I don't have this on here, but let's put part number 4. What if we heat the reaction? So this is exothermic, which means it's going to release heat. So if I increase the heat, it's going to counteract the fact that it's exothermic, right? Because right now it's releasing heat, and if I add heat to it, it's not going to want to make more products to release more heat. So by heating the reaction, it's going to shift left. All right, so let's take a look at a few other examples for the end of this chapter. So Friday when you come, you will bring your chapter 15 notes, and we'll put into action all the stuff about equilibrium and how it relates to acids and bases. So let's look at some more examples. Let's say I have this. I have dinitrogen tetroxide in equilibrium with 2 moles nitrogen dioxide. What happens if I add NO2 to the system? Well, it will increase the concentration of NO2 and force the reaction to shift left. Because at equilibrium, Q equals K. If I add NO2, right, if I write this out, if I increase the concentration of that, this whole fraction gets larger, so Q will become even greater than K. And when that happens, we have to shift left. And I could do the opposite. I could say, what if I removed, there's only 2 options. I'll remove NO2. Then using the same equation, this is now getting smaller, which means the whole fraction is getting smaller, which means now Q is less than K. So in order to counteract that, we're going to shift right to make more products. All right, let's take a look at something like this. Oh, these are all gases. What if now I have this reaction and I'm going to increase the volume? All right, so using our PV equals nRT reaction, I have increased the volume. Right. So I've increased the volume, so I've decreased the pressure. That increases, that decreases. So if I have decreased the pressure, right, at the same R and T, we're going to have to increase the number of moles to make up for it. We want more moles to increase the pressure back to where it was. So this reaction, right over here, we have 2 moles. And over here I have 4 moles. So if I need to increase the number of moles to get back to equilibrium pressure, I'm going to shift, in this case, back towards reactants. Because the reactants have 4 moles of product, or 4 moles on that side of the equation. All right, let's do one last example before the end of class today. Let's say I have this. All right, so now I have heat as a reactant. If I have heat as a reactant, that is the definition of an endothermic reaction. So if it's endothermic and I add heat, I will add more. Heat is really a reactant in this case. So if I'm adding heat, I'm adding a reactant, which will shift the reaction to the right. If I cool it off and I remove heat, I will take away some of the reactant, which means it'll now shift left to compensate for that heat that I'm taking away. And we could do the same thing for the endothermic reaction like we had on the previous example. All right, so now my exothermic. This may be more obvious when I write it this way. If I add heat, heat is now a product. So if I add more product, it's going to have to shift back to the left to compensate for that. Or if I remove heat, I cool it off. It will, if I remove this, it will shift towards products or shift to the right to make up for the loss of heat. So in the abstract, we have a lot of different tools at our disposal to figure out, are we at equilibrium? If not, what do we need to do to get to equilibrium? And how does manipulating the reaction affect the rate of products or reactants? We're going to use all that stuff when we talk about acids and bases, and we can figure out how an acid and a base combine together, what's the predicted product, and where are we in the equilibrium reaction of acids and bases. All right, so bring your Chapter 15 PowerPoints on Friday. We'll have an individual quiz, and email me if you have questions. I'll be more than happy to help you out. All right, have a great snow day, if in fact we have no class on Wednesday. Okay.